Assalamualaikum and good day. My name is Sabreena binti, a student from School of Mechanical Engineering, UiTM. Today, I will be presenting my final year project, which is the effect of fiber orientation on the mechanical properties of Kenaf Fiber Composite via ANSYS Simulation. This project was done with the help of Associate Professor Dr. Aida Jumahat. Now let us look at the overview of the presentation. Firstly, I will briefly touch on the introduction. After that, I will explain the research objective, the scope of work, and the methodology. Then I will share the results and discussion that I had obtained before I concluded my presentation. In the last few years, as the researcher had been starting to take interest in natural fiber reinforced polymer and FRP composite, as well as the increase in environmental awareness and concept of sustainability, the usage of an FRP composite for many engineering applications are gradually increasing these days. In this study, Kenaf FRP composite is chosen to be analyzed. Kenaf, with its scientific name Hibiscus cannabinus L, is an herbaceous plant that is first introduced in Malaysia in the early 1970s, and compared to other natural fiber, Kenaf has advantages due to its short plantation cycle and flexible environmental requirements. Kenaf fiber is usually taken from the bust of the plant and has recently been commercialized in industry as natural fiber reinforcement for composite for its appealing mechanical properties such as low in density but high in specific strength, impact strength, storage modulus, and thermal stability. The objective of my project are to evaluate the effect of fiber ply orientation on the tensile, compressive, flexural, and quasi-static indentation or QSI strength of Kenaf FRP composite, to examine the effect of hole in the tensile and compressive strength of the composite, and to study the effect of supporting triangle 0-degree fiber orientation on tension, compression, flexural, and QSI properties of the composite. Next is the scope of work for my project. The first scope of work is conducting a literature review on previous study related to NFRP composite, Kenaf fiber, and the effect of fiber orientation on the mechanical properties of the composite. The next scope is conducting modeling and simulation to analyze the performance of Kenaf FRP composite using ANSYS software. And the last scope is simulating glass FRP composite for validation purposes by comparing results obtained for both Kenaf and glass FRP composite. Now let us look at the ANSYS simulation steps in methodology. The ANSYS simulation starts with setting up the element type, creating the specimen model, and then setting the input data for material properties and failure criteria. Then sectioning and meshing were done on specimen model. The steps were then continued by defining the boundary conditions and load before solving the simulation. The specimen size, taking sequence, and the input data of mechanical properties and failure criteria used in ANSYS simulation are shown in this slide. This slide shows the boundary conditions, load, and meshing used in tensile, open hole tensile, compression, and open hole compression. All four tests use quadrilateral map mesh with the size of 1 mm. This slide shows the boundary conditions, load, and meshing used in flexural test and QSI test. Both tests use quadrilateral map mesh with a size of 8 by 8. Let us look at the first finding of the project, which is the effect of fiber orientation. This slide contains exponential graph of maximum tensile stress, maximum compression stress, and maximum flexural stress, as well as a polynomial graph of maximum quasi stress against fiber orientation. It was observed that tensile, compression, and flexural tests projectile the same behavior against fiber orientation, in which the highest maximum stress was obtained at 0-degree fiber orientation and the lowest value was obtained at 90-degree fiber orientation. The result indicates that specimen tested under tensile and compression loading parallel to the 0-degree fiber orientation exhibit greater strength as the specimen start failing with rupture of the fiber reinforcement followed by the bonding of the fiber matrix interface. Meanwhile, under transverse orientation, they fail with rupture of fiber matrix interface only. On the other hand, when the specimen with 0-degree fiber orientation was tested under flexural load, the load was perpendicular to the fiber orientation, thus small fibers were able to carry the load. Contrarily, the highest maximum quiescent stress can be seen at 45-degree fiber orientation, while the lowest maximum quiescent stress is seen at 0-degree and 90-degree fiber orientation. A previous study suggests that at 45-degree fiber orientation, both fibers and metric play a significant role in resistance offered to shear-induced damage, thus causing it to possess the highest maximum quiescent stress. This slide shows the deformation contour for every test on Kenaf epoxy composite to show its deformation behavior. It can be seen in tensile tests, the specimen elongates in the direction of the load before fracture. Meanwhile, under a compression load, the length of the specimen is reduced. As seen from the front view of the specimen under flexural load, it was observed that the specimen experienced bending in the direction of the exerted load. Meanwhile, the highest indentation depth was observed at the middle node of the specimen where the QSI load was introduced. The next finding is the effect of open hole on FRP composite. OHT and OHC testing provide valuable data for the allowable strength of FRP composite assembled with fasteners or to stimulate a flow in the composite. This slide shows the effect of open hole on the maximum tensile stress of glass epoxy and Kenaf epoxy composite. It was observed that the maximum tensile stress was decreased in the presence of open hole on the specimen. From the table, it can be seen that the highest reduction displayed at 90-degree fiber orientation. The same effect was observed on the maximum compressive stress of FRP composite, in which the highest reduction was shown at 90-degree fiber orientation, showing that transverse fiber orientation is highly affected by the open hole and possesses the lowest strength on retaining stress in the tensile and compression direction. The results suggested that at 0-degree fiber orientation, which exhibit the least reduction and the highest maximum stress in the presence of open hole, are due to the high amount of fiber that existed in the direction of the load for both tests. This slide displays the effect of an open hole on its deformation behavior under tensile and compression load at 0-degree fiber orientation. Under tensile load, the specimen elongates and the circle shape of the hole stretches into an ellipse shape in the tensile direction. Meanwhile, as compression load is exerted on the specimen length shortens and the circle shape flattens into an ellipse shape in the transverse direction. The effect of open hole size on maximum tensile stress and maximum compressive stress was studied on specimens with unidirectional 0-degree fiber orientation. The open hole size tested was 6 ml, 8 ml, and 12 ml. It is observed that as the diameter of hole size increases, the maximum stress decreases. The same behavior was observed on both maximum tensile stress and maximum compressive stress towards an increase in hole size diameter on Kenaf epoxy composite with a reduction percentage of around 17% for 6 ml, 34% for 8 ml, and 53% for 12 ml hole compared to unwhole specimen. The results indicate that the specimen with larger hole size lessen the stress supporting region, whereas specimen with smaller hole size contain larger region in which stress could be disseminated, thus reducing the damage on the specimen. The last finding is the effect of addition of supporting ply angle on FRP composite. It can be observed that the maximum stress elevated with the addition of 0-degree fiber orientation in the layup sequence of the composite. The figures display that the addition elevates the maximum stress significantly at 90-degree fiber orientation with a percentage increase of 199% for both maximum tensile stress and maximum compressive stress, 33% for maximum flexural stress, and 25% for maximum quiescent stress. The result indicate that the addition of supporting ply angle into the layup sequence give great influence on Kenaf epoxy, especially in terms of its maximum tensile stress and maximum compressive stress. This slide shows the effect of addition of supporting ply angle on the maximum deformation contour for 90-degree fiber orientation of Kenaf epoxy under tensile, compression, flexural, and QSI loading. Influence of geometrical alterations such as fiber orientation, presence of open hole, and addition of supporting ply angle 0-degree on the mechanical behavior of composite in terms of its tension, compression, flexural, and QSI properties were investigated. It was found that 0-degree fiber orientation exhibit its highest maximum stress under tensile, compression, and flexural load owing to the presence of more fiber to carry the load. Meanwhile, the highest maximum crustal stress can be found at 45-degree fiber orientation, where both fibers and matrix resist the shear-induced damage from the load. The presence of open hole decreased the retaining strength of composite and was also influenced by the fiber orientation. 90-degree fiber orientation exhibit the highest reduction in the maximum stress under both tensile and compression load. Meanwhile, 0-degree fiber orientation was the least sensitive towards the open hole. The open hole size diameter influenced the ability of stress to disseminating on stress supporting regions, in which larger open hole size will reduce this region, thus reducing the maximum stress. The addition of 0-degree fiber orientation into the lamination scheme shows a significant elevation effect on the maximum stress, especially at 90-degree fiber orientation for all four tests. To conclude, Kenaf FRP Composite shows great potential to be implemented as a partial substitute for conventional FRP composite due to their valuable properties such as good mechanical properties, biodegradable, low cost, and sustainability. With that, we reach the end of my presentation. The references used for the presentation are included in the next slide. For any inquiries, you may contact me from the contact info as written below. Thank you for listening and Assalamualaikum.